Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we are going to work on graphing trigonometric functions, the reciprocal trigonometric functions. So that's going to be the cosecant, the secant, as well as the cotangent function. So again, these are the notes that I went through my class, and what I'm going to do is just kind of work through this lesson one more time, so therefore I can have some answers for you and for them. So basically, we're just going to learn, where these graphs come from, how they kind of relate to sine, cosine, and tangent, and then how to find the parts. So again, just again, a warning, I'm not actually graphing them. I used to teach that, but it just took us so much time to actually plot the points and everything. And, eventually I realized we don't really need, I didn't really think it was very beneficial for my students to spend so much time on the graphing, especially when we have graphing technology. So now we really kind of focus on our understanding as well as being able to identify the particular parts, like domain, the range, the asymptotes, domain, and the period. All right, so therefore what I did is I kind of started this lesson looking at the sine function. So last class period, we obviously learned how to graph sine, cosine, and tangent. And so what I did is I gave the students, all these points, and they plotted the sine function. Again, my scale is not perfect. These are not supposed to be evenly apart from each other. That's just the scale that or just how the graph that I used. But either way, they went ahead plotting these points. Now, so students at least had an understanding of where the red graph, which is the sine graph, came from. Well, then what I did is I asked them, well, why don't we go ahead and find the cosecant? And rather than doing the cosecant for each and every one of those points, let's just do the first quadrant. So, I basically asked them to do the cosecant of 0, cosecant of pi over 6, cosecant of pi over 4, cosecant of pi over 3, and the cosecant of pi. Now, again, oops, I didn't kind of show that, did I? I guess I should probably, let's go and do that. I'll draw that right here. So obviously we can draw the sine graph really quickly just by using these 4 points. Like if you know 0, like sine of 0 is 0, and then at pi halves you can see it's at 1. And again, sine represents the y coordinate for a point on the unit circle. At pi we're at 0 and 3 pi halves. But let's go ahead and do the first quadrant here, because I said, all right, let's just do the first quadrant. So we know this point, that's 0, 1. Then we had at pi over 6, that coordinate point is square root of 3 over 2, 1/2. Then we had pi over 4, which is square root of 2 over 2, square root of 2 over 2. And then at pi over 3, that's going to be 1/2, square root of 3 over 2. Okay, so that's where I got these first 4 points, because that's what I wanted just to focus on, was these first points. So again, we're looking at that's the wrong graph. That's 1, 0. Oh, and then we did this one as well. Okay, so we found the sine, and I kind of reviewed students with the sine, and then I asked them to find the cosecant, which is, again, remember the sine of an angle, sine of theta, right, is equal to the y coordinate. So the cosecant of theta is equal to 1 over y. And I said, all right, well, then just go ahead and reciprocate, and do this. But I mentioned to the students that, not always is just putting something over 1 the easiest thing. Like 1 over 1/2, just gets simplified to 2 over 1, which equals 2. Now, again, that's not usually too bad. But again, what about when you have 1 over square root of 2 divided by 2? You don't want to multiply by the reciprocal on top and bottom, then rationalize the denominator. So what I reminded them is, remember the reciprocal, yes, you can always write something as reciprocal as putting it under 1, but go back to our roots. Sine of theta equals opposite over hypotenuse. And remember cosecant of theta, this is again for a right triangle, not for points on the unit circle. But so cosecant was going to be the hypotenuse over opposite. So again, yes, y and 1 over y is a reciprocal relationship. But again, when you have fractions, just flip it. So rather than doing 1 over square root of 2 over 2, just do 2 over square root of 2. And then you should hopefully recognize how to rationalize the denominator, and you get square root of 2. So for cosecant of 0, if I take the reciprocal of 1 over 0, that's going to be undefined. The reciprocal of 1/2, you can see my work there, or just flip 1 over 2, flip it to 2 over 1, which equals 2. Square root of 2, we recognize that to be the square root of 2. And then 2 radical 3, when you rationalize that, so therefore you have 2 over square root of 3. Rationalize the denominator, you get 2 radical 3 over 3. So then what I said is, all right, let's plot these points for you guys. So obviously, the easy one, 1/2, that's going to go to 2. All right, pi over 4, which was square root of 2. That's roughly like 1.3-ish. And then this 2 radical 3 over 3 was like 1.1. So you can see how those points kind of relay right there. And then at pi halves, you know, the sine is 1. And the cosecant of pi halves is going to be 1 over 1, which is also 1. So they share this point. There's actually, that's true for sine as well as for cosecant. Well, I also asked them to do, did I not write that in there? Oh yeah, I did do cosine of pi. Then I also asked them to do cosine of pi in addition to this cosine 0, because how do we represent this when it's undefined, right? And when it's undefined, we know that there's going to be a vertical asymptote. So again, I didn't write this point, but you can see at pi, it's going to be a vertical asymptote. And that is also going to be true for 2 pi. But my main goal was for students to kind of look at this graph and see, like, what is the relationship with these blue points and the red points? And a lot of students said, you know, it's flipped, it's the, you know, inverse or, you know, reciprocal or whatever else. And like, yes, it's, you know, those are all some words that I think carry some weight to this description, you know, but I think one of the ones that really stuck with me was like that mirror image, right? It's kind of like, here is, you know, you could say like a little hump going down, and then this is the one reflecting up. Now, it's very important to understand these are not the same, right? Because again, we have vertical asymptotes here. So this blue graph is approaching the vertical asymptote, where the sine graph actually, you know, intersects at 0. So there, you don't have the perfect curve. And when we actually look at the graph on the decimals, you'll be able to see. But the general kind of relationship is like that mirrored image. They share a coordinate point, a vertex, right? A maximum or a minimum, which depending on which graph you're talking about. But then they kind of go in the opposite direction, like a mirrored image of each other. And you can see that kind of works again over here. Then the other kind of, then we started looking at, all right, well, let's talk about the relationships here of this cosecant graph. Well, if you kind of follow the pattern, like this opens up, then it opens down, then you can say the next one is going to be, you know, up here, right? I mean, it's going to open up. So you can see it starts to repeat itself. So therefore, the distance that the graph is going to take to repeat itself is going to be 2 pi, right? It's just like sine. So sine and cosecant have the same period, right? 2 pi. And again, that's the same thing. If you're going to look over here, like this graph is now going to open down, right? So this opens up, then it's going to open down. So therefore, that helps us understand the symmetry. It's not going to be symmetrical about the y-axis, but it's going to be symmetrical about the origin, just like the sine function. So sine is odd, so is cosecant is odd. And again, that's something we're going to talk a lot more about in the next chapter. Let's see what else was happening here. You can see that the graph changes from decreasing to increasing, and therefore we have this little minimum point, right? And then we have an asymptote, and then it's increasing to decreasing. So we have a little maximum. But these are not the lowest points or the highest points of the graph, right? They're just the lowest or the highest points on a particular interval. So you can see these are what we call relative, again, minimums and a relative maximum. They're a high point or a low point, but they're not the absolute highest and the lowest points. We can also take a look at the range. Now, the range is very interesting. So, you know, the sine graph, we have this range is contained between -1 and 1. And the blue graph looks like it's kind of like that mirrored image of that. And I think this is really important, especially when we get into these problems. It's really important to kind of see that you can see this mirrored image of, you know, so if the range is from -1 to 1, the blue graph is from -infinity to -1. But again, it includes -1. And then from 1 to infinity, which includes 1. So it's really important to understand that kind of that mirrored image kind of shape or what's going on, because that helps us identify the range. In terms of the domain, you can see that we have asymptotes. So the domain is no longer all real numbers like the sine graph. However, we do recognize that the asymptotes occur when sine of x is equal to 0, right? Those are like the zeros or the solutions. Kind of interesting. Again, that makes sense, right? Because when y is 0, then cosecant is going to be undefined, looking at the unit circle there. But again, we can see, well, not only do the asymptotes, you can see that they occur at every 0 to pi, to 2 pi, 3 pi, and then 4 pi, and 5 pi. And therefore, I can write a relationship for those asymptotes to be every pi n, right? On every pi, there's going to be an asymptote. So if I wanted to write an algebraic statement for that, I would say x equals pi n, which obviously we're going to do. And the domain is just going to be all real numbers except for those asymptotes. So I think that is just about it for the cosecant function. We talked a lot about it, and then we kind of skimmed over the secant. Because it's really, guys, kind of the same thing, right? You can see we basically just take the cosine graph and then we just kind of do the mirrored image. Now, at least as far as this initial period, you can see the cosine kind of gets like cut off here and here. But again, like you hopefully recognize that it's going to continue over this way and it's going to continue over that way. But continuing over this way, we can recognize that the graph is going to be even, just like the cosine function, right? Cosine's even, secant is going to be even. The other thing that's kind of different with cosecant is where the asymptotes occur. So again, the period is 2 pi, but the asymptotes occur every pi, right? When they start at pi halves, and then pi halves plus pi gives you 3 pi halves. So the asymptote equation for this is like tangent. If you remember tangent, the vertical asymptotes occurred at pi halves plus pi n. Well, secant occurs the same thing, pi halves plus pi n, because to get to the next asymptote, I'm going to have to add pi again, and add pi, and add pi, or subtract pi, basically just meaning n is going to be negative. So it is even, and so between these two functions, you know, this one's even, symmetrical about the y-axis, and the asymptotes are going to change. However, that mirrored kind of relationship, the range and domain, or the period, is all going to be really exactly the same. So then we get into the last one, which was the cotangent function. So if you remember, this red graph was this initial kind of period between 0 and 2 pi. And actually, I don't know why I didn't graph the, let's see, 3 pi halves. This would have been 2 pi. So if you remember, I kind of did my best little S curves that I could possibly do here. But again, to understand tangent, like the easiest thing to recognize, or at least, you know, when I told the students, like when you're trying to understand, like, you know, which graph is which, when is it undefined, when is it defined, the best points that you can use or to think about is this quadrant, or is this unit circle, just with those 4 points. Like just with these 4 points, you can determine when when cosecant, secant, and cotangent is going to be undefined, including tangent. Because remember, they're only going to be undefined when you're trying to divide by 0. So, for instance, tangent at 0 degrees, right? We graph this point. We did the same thing with the other graphs for tangent. And we say tangent is y over x. Well, 0 over 1 is just going to be 0. You can see that point. But now when I do cotangent, which is with the reciprocal, which is 1 over x, or 1 over 0, I'm sorry, you can see that graph is now undefined, which for whatever reason, I did not put an asymptote there. So let's put an asymptote there. So you can see at 0, now the graph is going to be undefined, right? And then let's go and look at pi halves. So at pi halves, tangent was undefined, right? Y over 0 is undefined. But yet now when I look at cotangent, 0 over 1 is defined, which is at 0. So you can see why for the cotangent function, that's why I have now an x-intercept there. And then again, going to pi, just trying to do this initial period here. So for at pi, again, negative 1 over 0 is undefined. That's why I have an asymptote. So we have an asymptote at 0. We have an asymptote at pi. We know the graph crosses at pi halves, but do we know what this graph is going to look like? Well, a couple other points that kind of stem out, or at least the one important point that stems from this, is pi over 4. Because at pi over 4, tangent and cotangent are exactly the same. It doesn't matter if you do y over x or x over y. They're both 1. So you can see how they share the point pi over 4, 1, and how they share the point 3 pi over 4, negative 1, right? But that's where really the similarities, you know, end, because remember, they still have that mirrored image, that reflection kind of idea going on. So if I kind of take that into consideration, and obviously you could plug in these points, you could obviously do the reciprocals, plot them if you wanted to. But what I did is I just kind of took that relationship and I plotted them over here, and therefore I just draw my nice little curve. So you can see how this graph kind of shows it, kind of like declines. All right, so let's go and take a look at the differences here then with tangent besides just the curve. Well, tangent looks like it's always increasing, right? Except for where the asymptotes are, the graph is always going up. Whereas cotangent is kind of the exact opposite. It's always decreasing or going down from left to right, except for where the asymptotes occur. Obviously, the obvious one, wherever x is defined, tangent is undefined. Wherever tangent is defined or undefined, cotangent has an x-intercept. The domain, or the time, how long it takes the graph to repeat itself, looks like it's going to be pi, right? So from here to here, and then it looks like the next one is going to be, again, from pi to 2 pi, it's going to repeat itself. So the period is just like tangent. It's going to repeat itself. And one thing I mentioned is the, let's see, it also looks like it's odd, just like tangent. Tangent was an odd function, symmetrical about the origin. What else were we going to talk about? We were going to talk about the domain, or the asymptotes. You can see that the asymptotes don't occur every pi halves plus pi n. These blue graphs actually occur every at 0, at pi, at 2 pi. So it's kind of like cosecant. They occur every pi n. So that will be important when we are writing the domain. And then again, just like the tangent, the range, you can see this graph is going to be from negative infinity to infinity. Doesn't matter what the transformations are, that is going to be your range. All right, so basically, we kind of looked through these, and then I just kind of had students, kind of talk about that. And then we just kind of spent, one more time looking at these graphs so you can see this relationship, not from what we did on the board, in my class, or what I just presented to you, but actually looks at a graphing calculator and kind of see these differences actually in there. So let's just go and take a quick little look just to kind of confirm everything. All right, so looking at the sine function, this is what we did before. We graphed the sine, and, again, just to make sure you understand, domain is all real numbers, all right? And you can see the period, goes into 2 pi from there. So let's go and take a look at the cosecant function. Now, again, remember, that Desmos is not going to give you the asymptotes, right? We need to understand where those asymptotes occur, but you can kind of see it looks like it occurs somewhere right around here, which coincidentally kind of looks like it's at 3.14 or pi, right? And you can see like that would make sense here. And again, like you can even have a little fun if you wanted to, x equals pi right there. And you can see like, yeah, that looks like that'd be an equation for an asymptote. But again, the important thing is, remember, sine is not a part of the graph. We just use sine to represent that they both share the points, pi halves 1, and they share all these points. But when we're actually graphing cosecant, if you needed to graph cosecant, or when we're just identifying the characteristics of cosecant, the sine graph is not there, right? So, but I just wanted you to see that reciprocal relationship. Again, see how their periods, it repeats every 2 pi, just like sine, but it has asymptotes, which sine did not. And you can see this relationship is exactly the same for cosine. Okay, and again, cosine is actually not there, right? So it's just using that for that reciprocal relationship. Now, the tangent and cotangent is not really as easy to kind of view. You can see there's the tangent. You can see how the graph repeats itself. If you remember, that was our initial period from negative pi halves to pi halves. And cotangent, obviously, is, again, from 0 to pi, right? So you can see, again, that pi, it's defined for x, and you can see that's where we're going to have that asymptote occur, right? And again, but you can see at least that they share the point pi over 4, 1, 3 pi over 4, negative 1, and then they also have that inverse relationship, that mirrored relationship. And again, it's not a perfect mirrored relationship, right? Just like I explained here, when you actually look closely, you can see that it's not a perfect mirrored relationship, right? It's not whatever's down here is going to be exactly up there because, again, there's an asymptote here. This graph crosses at pi halves, and this is going to approach x equals pi halves. So it's not going to be the exact mirror image, but you can kind of get the idea of that relationship, okay? So that's what I wanted students basically to come away from right here. So let's go back and look into now generalizing all of these characteristics. So when generalizing the characteristics, we basically just look at the transformations. And so I just reviewed the students the same slide that I used for sine, cosine, tangent, which is really the same slide that I used for all the 12 basic trigonometry functions. It does not matter what the function is. It doesn't matter if I'm talking about cosecant, the absolute value of x squared, sine of x. It doesn't matter what the function is. These a, b, c, and d are all going to impact your graph the exact same way, right? And I didn't even write them down like I did in the last chapter because, again, I told students it's the exact same notes. A stretches and compresses your graph vertically. If a is less than 0, it's a reflection about the x-axis. B, horizontally stretches and compresses your graph. When B is negative, it's a reflection about the y-axis. C is going to be your horizontal shift. In this case, we call that the phase shift, right? And D is going to be your vertical shift or vertical translation, which is again, is shifting your graph up or down. So I did provide a calculator if that's something that you want to kind of play around with, just to, it hasn't really sunk in, which for a lot of students, for my own students as well, it didn't really they still needed to kind of see it. So I provided it for those of them that needed it, but for majority of them, this is the third time we've kind of covered this. So they already kind of had a good idea of what to expect. All right, so here's the cosecant graph. Now I put these on two different slides because I wanted to provide I wanted to give students the parent graph for each of them. But in reality, the cosecant and the secant have exactly the same piece of information. Their period is both 2 pi. The phase shift is C. The vertical shift is D, right? The range is kind of look confusing, but I'll talk about that. But again, you can see the range, they're both have a relative maximum of -1 and a relative minimum at 1. So their range equation is right there. I didn't tell students, I said you could write it down if you wanted to, but I'm going to use a different approach when we actually do the problems. And then the only really difference between them, besides their graphs, is their vertical asymptotes and domain. Because again, for the cosecant, you can see the vertical asymptotes appear at x equals pi n. So every pi n, or every pi, right, n could be any integer, there's going to be an asymptote. So the domain is basically all real numbers except for pi n. So this is the initial period. Again, I provided the sine graph as the dashed line. It's not a part of the graph. That's why I changed the colors. But I just so therefore you could kind of see again where those points and everything comes from. Then we did the secant, which again is very similar, same kind of idea. You can see the same information. The only difference is, obviously, besides the initial period being different of the graph, you can see the vertical asymptote occurs at pi halves. Plus pi n, and therefore the domain is going to be all real numbers except for pi halves plus pi n. But yet the range is exactly the same, right? It has that relative maximum of value of -1 and that relative minimum value of +1. All right, and then cotangent, we could kind of put this side by side. I used to actually teach tangent and cotangent kind of together because you can kind of see side by side how they're just that reciprocal relationship with each other. They both have a period of pi. Right? So this is pi divided by absolute value b. C and d remains the same. The range is different, right? This is like tangent, -infinity to infinity. And the vertical asymptotes and domain is just like the cosecant function, where it's going to occur every pi n. And this is going to be our initial period. All right, so now that we got that done, let's kind of go through what we're going to do. Again, guys, I'm not going to be graphing them, even though I know it says graphing, but hopefully based on all of this information, you can go ahead and provide a rough sketch of what the graph would look like. And typically that's what I tell my students is they should be able to provide a rough sketch of what this graph looks like, basically, or at least the initial period. And we used to had students, they had to graph 2 periods. But, I think just the amount of time that I spent teaching students to graph and helping them with graphing, I think we could have spent that time doing a lot of other things. And then again, they knew how to graph, but then they didn't understand the range or they didn't understand the vertical asymptotes, which becomes very important in other lessons. So it was like, well, why are we, focusing on plotting some points when they don't understand some other key information? All right, so the first example is, let's just kind of go through this because there is some kind of tricky parts on this that I am going to discuss. And I guess I didn't finish this. So the first one is period. That's pretty easy, right? If you look at your notes that I did, 2 pi divided by b. Remember, x over 4 is the same thing as 1/4 x. So 2 pi divided by 1/4, multiplied by reciprocal, 4 over 1 on top and bottom, and that's how we got 8 pi. We have vertical shift up 1. And the range, so the way that I like to teach range, I don't like to use that formula. I like to think about what is the range of the cosine graph, right? Because remember, these are just reciprocals of each other, right? They have that mirrored image. So the cosine graph with no transformations is from -1 to 1. When I multiply that by 2, when I have an amplitude of 2 of cosine, that's now going to go from -2 to 2. This is something we talked about last class period. So now my range of this cosine graph, again, this is what I'm talking about right here, is from -2 to 2. Now the graph is being shifted up 1. So now the range is from -1 to 3. So if I can figure out the range of cosine, I can figure out the range of cosecant. Because again, like here is the cosine. Like if I know what that range is for the blue graph, I can figure out the range of the red graph, which is basically going down to -infinity to the low point, and then, or to the low point of sine, and then going from the high point of cosine, sorry, not sine, cosine, and then going up to infinity. So that's how I got the range. I know that the low and high point of the cosine graph is -1 to 3. So my range is going to be from -infinity to -1, and then from 3 to infinity. The vertical asymptotes, again, is interesting. So we got to understand, how are vertical asymptotes going to be impacted? Well, if you have a graph with vertical asymptotes, when you stretch or compress, that doesn't change the asymptotes. When you shift up or down, the asymptotes remain the same. The only thing that's going to impact the asymptotes is when you're stretching or compressing or shifting the graph left or right. So we got to look at this function and we say, all right, the graph originally had a period of 2 pi. It just got stretched, horizontally stretched, to 8 pi. Right? So my asymptotes are going to change. And again, I'm not going to pull this up, but if you want to look at it, a lot of times for students, when they would kind of give me that confused look, I would pull up the calculator and be like, hey, see for your own eyes what's happening here. See for your own eyes why the asymptotes are changing. So if that's kind of something where you're at, click on the link, look at the Desmos. I put these 2 equations in there, so therefore you could kind of visualize and see that. All right, so we have x over 4 equals pi halves plus pi n, and then to the 4th. Good. So to find the vertical asymptotes, all you're going to do is take whatever's inside the function, because remember, inside the function is your horizontal transformations, right? So in this case, we just have x is being divided by 4. So I'm going to write x divided by 4, and then you just solve for x. So the original asymptote equation, so you set whatever's inside your function equal to where the asymptotes occur. Now again, you only have 2 equations for your asymptotes, right? It's either pi halves plus pi n or pi n. So how do you know which one? Well, you can either memorize them, you could guess, or my preferred method is just to use remember those 4 points on the unit circle? If you know those 4 points on the unit circle, you can identify when the secant is going to be undefined, and then hopefully understand it's either going to be at pi n or it's going to be undefined at pi halves n. And obviously it's going to be undefined at pi halves plus pi n. So you set it equal to the asymptote equation. To undo divided by 4, I multiplied everything by 4, and I got x equals 2 pi plus 4 pi n. All right, so for the next example, it's really important, again, that A, B, C, D formula. This is not written in that A, B, C form, right? My unknown is x. I want that to be written in front. So I don't even know what my B is in this case. So what I'm going to do is I have a negative out in front. That's a reflection of the x-axis. But I'm going to rearrange my variable and pi, right? X is the variable. And then I need to factor out the negative. So therefore, I can see that actually I'm not shifting the graph pi to the left. I'm actually shifting the graph pi to the right. And I have a reflection about the y-axis. So that negative tells me a reflection about the y-axis, and the graph is being shifted right to pi. Now, it's important, again, on this one to understand that the graph is being reflected about the x-axis, reflecting about the y-axis, which is really reflecting about the origin. And, just a little, again, reminder, cosecant and cosecant is odd. So it's symmetrical about the origin. So actually, those reflections aren't going to have any impact on the graph. It's still going to look exactly the same if you needed to graph it. The range, again, I looked at the sine. So again, notice that there's really nothing that's happening that's stretching or compressing the graph or shifting up or down. The only thing that's happening is sine graph is from -1 to 1. Then the graph is just being, flipped, right? Well, that doesn't change the, the range for that function. It's still going to be from -1 to 1. So in this case, I can write the range from -infinity to -1, union 1 to infinity. The last thing that kind of comes up in this case is going to be the vertical asymptotes. So again, I don't know why I didn't do this, but let's just go ahead and set what's inside my function equal to my asymptote equation, which is pi n. But this one does involve definitely some explanation, so I'm kind of glad that this happened. So if I could add x, right, you could subtract pi and then divide by -1. But let's just go and do this. X equals pi n plus x, and then subtract pi n. So my asymptote equation is x equals x equals pi minus pi n, which is the same thing as x equals pi n. And students really get confused in this. How is this equal to that? But again, I think about this like there's a couple of different ways I explain this. One, I know the asymptotes occur every pi. So if I shift the graph over pi units, right, which is my transformation, the asymptotes are going to remain the same, right? I mean, if I have an asymptote at every pi, right? So let's say I have an asymptote, or let's just say, so if I have pi and then I shift it over pi, well, whatever pi was at 0 is now at pi. Whatever pi was at pi is now at 2 pi. But again, like I'm actually not changing the intervals of where pi occurs. And then the other thing is I had a reflection. Reflection is not going to change those asymptotes either. Now, another way to kind of think about this is like identifying, even numbers. I could say all even numbers can be represented by 2n, and where n represents any number, right? So, n could be -4. -4 times 2 is -8, was even. We could say n could be 5. 2 times 5 is 10, even number. I could also say all even numbers can be represented as 2 plus 2n. So again, we recognize though, if I have an even number and I add 2 to it, that's still going to give me an even number, right? It doesn't matter what the number is. If it's even and then I add 2 to it, it's still going to be even. But that adding 2 is redundant, right? So that's what the case here is. If I have pi minus pi n, right? Well, again, n can be positive or negative. So therefore, we don't really need it to be a negative pi n. Like negative pi n is really the same thing as positive pi n, right? Because n can be positive or negative. Typically, we like the positive version is more simplified. We'll see those more on a multiple choice kind of section. And then if I have pi n, but then I'm adding pi, like again, why do we need to add pi plus pi n? We could just use pi n, and that's going to represent all the intervals. So that's kind of how that works. I told students, I accept this for these two for this chapter, but once we get into the next chapter, it's going to be important and helpful to understand that simplified version. All right, so now let's get into the fun stuff. So we're not actually going to graph, we're just going to identify all of the parts. Okay. So the first one is, let's just go and find the period. The nice thing about here is my b is just 1, right? So period is just going to be 2 pi. I am not adding or subtracting inside, right? Again, a lot of students are like, where, is it -2? Well, again, that's why a lot of times we use parentheses to differentiate that. So I have a vertical transformation or vertical shift down 2. The range, again, I'm just going to look at the sine graph. So the sine is from -1 to 1. Multiplying by 2 takes it from -2 to 2. And then the graph gets shifted down 2. So now the range is going to be from -4 to 0. So my range here is going to be -infinity to -4 included, right? And then all the way from 0 to infinity. As far as the vertical asymptotes go, there's nothing changing around the inside, right? So now I just need to remember what the asymptotes are for cosecant. And again, like here's if you like forget, right? Like crap, what was that equation? Well, again, here's 2 points. It's really actually going to be these 2 points. Which one of these is undefined for the cosecant? That's 1 over y. Oh, that's 0. And again, it's also going to be undefined here. So that's going to be 0, pi, 2 pi, 3. Oh, that's going to be pi n. So my vertical asymptote is equal to pi n. No transformations, fairly basic, good to go. The next one here, automatically when I see a negative, I always like to write the reflection because I will forget it and most students would forgot it when they wrote their answers on the board. So let's just do this as a reflection, the x-axis. Our period is going to be 2 pi divided by 4, which equals pi halves. My range is, again, remember for cosine, right? It doesn't matter if you have the reflection. So the -2 doesn't really impact anything. But now it's going to be from -2 to 2. And that 4 is a stretch or compression, or it's a horizontal compression. So that's not impacting the range. So my range in this case is going to be from -infinity to -2, union 2 to infinity. However, the vertical asymptote, that is going to be 4x equal to, again, for secant, that's going to be pi halves. Secant, again, is undefined at pi halves, and then plus pi. So that's going to be pi halves plus pi n. Okay, so now I just need to divide by 4. And again, remember, dividing by 4, guys, is the same thing as multiplying by 1/4. So you could also just multiply everything by 1/4 there. And we get our vertical asymptote is x equals pi over 8 plus pi over 4n. And again, you can see there's nothing redundant here. And this would be like kind of our simplified answer there. And yeah, simplified answer, and we got a reflection, we got everything. Sweet. All right, move on to the next one. Next one, we see that there is no stretch or compression. And there's our b again, in this case, is going to be 1. So our period is going to be 2 pi. We have a vertical shift or transformation of up 1. And we have a phase shift of right pi halves. Okay, so we have, that's going to be going right to pi halves. As far as the range, so again, for sine is from -1 to 1, but if I shift it up 1, now it's going to be from 0 to 2. So again, the cosecant is just that mirrored image of that range. So the range here is going to be from -infinity to 0, union 0 to infinity. And then let's see here. Vertical asymptote. So for the vertical asymptote, again, we got to set this is going to be x minus pi halves equal to pi n. So to solve for x, we're just going to add pi halves to the both sides. Now again, you can't add pi halves to pi n, so my vertical asymptote is just going to be x equals pi halves plus pi n. And that looks like it's going to be, can't really simplify it or of any of that case, so therefore that's going to be good from there. All right, last one. Now in this case, we don't have this, we have a b, but it's not factored out. So that's the first thing we're going to want to do is factor out. And again, remember, factoring out a 2 is like dividing both terms by 2. And dividing both terms by 2 is like the same thing as multiplying by 1/2. So sometimes explaining it that way helps students understand that when you factor out a 2, you're going to get x minus pi over 4. Because a lot of students, they just don't like factoring, right? But factoring is the same thing as dividing. And dividing is the same thing as multiplying by the reciprocal. And again, you can always check your work. 2 times x is 2x. 2 times pi fourths is pi halves. So therefore, in this case, we can see that the graph is being, there's no reflection, right? But we can see that the graph is being shifted. So we have a let's do period first. So period, in this case, is going to be 2 pi divided by 2, which is equal to pi. So my graph is being horizontally compressed. I have a phase shift of pi over 4 to the right. And that's it. So the range, again, the graph is not being stretched or compressed or shifted up or down. So the range is just going to be the that mirrored image of cosine. So cosine is from -1 to 1. Again, nothing vertically happened. So therefore, the range is just going to be from -infinity to -1, union 1 to infinity. And then my vertical asymptote, this one's going to be a little bit more work. So again, we're going to set whatever's inside our function. You could use this simplified version if you wanted to, or you could use, just the original equation, 2x minus pi halves equals secant is going to be pi halves plus pi n. So when I add pi halves to both sides, pi halves plus pi halves is going to be pi. So it's going to be pi plus pi n. Hopefully you recognize that we don't really need the pi here, right? Like pi plus pi n can just be written as pi n. So you could divide by 2 on both sides, but let's just get rid of the pi. We don't need it. So hopefully for students that are maybe just looking at the answers, where'd the pi go, right? But again, it's redundant. It's like 2 plus 2n. We don't need the 2. So then you divide by 2, and you can say x equals pi halves n. And so I'll just say vertical asymptote is x equals pi halves n. All right, now let's go and look into cotangent, which is basically, again, guys, the exact same process here. The only really difference is obviously the range. Oh, I didn't do the domain, did I? Did I say to do the domain? No, I didn't say to do the domain. But again, just a little FYI, the domain is going to be all real numbers except for where those asymptotes occur. So it's really the same kind of idea. You just write domain all real numbers except where those asymptotes occur. All right, for the cotangent, though, I asked for the domain and the range. And again, but the nice thing about the range here is the range is going to be all real numbers, right? Always, doesn't matter what's happening. It's all going to be all real numbers. And the domain is going to be all the values except for where the asymptote occurs. All right, and just, so again, notice that the period is going to be pi instead of 2 pi divided by b. But in this first example, we recognize that the equation is not in our standard form for transformations. So I rewrite the, x divided by 2 as 1/2 x, and then I'm factoring out of 1/2. Again, factoring out of 1/2 is like dividing out of 1/2, and dividing by 1/2 is like multiplying by the reciprocal. So if you multiply by 2 on both of these, you get factored out 1/2, and then you're going to get x plus 2 pi. And again, check your work. 1/2 times x is 1/2 x. 1/2 times 2 pi is pi. There you go. So we have a negative on the outside. That's a reflection about the x-axis. Our period is going to be pi divided by b. Again, multiplied by the reciprocal on the top and bottom, you get 2 pi. We can see here we have a phase shift pi halves to the left. Our range is negative infinity to infinity. And then for our vertical asymptote, we're going to take whatever's inside of our function. In this case, I just used this version, but you could use this version or you could use that version. It doesn't matter. And you set it equal to your vertical asymptote equation, which is pi n. So I subtracted pi, which you don't really need, right? So in this case, I didn't simplify it. I left it in there. But again, like if you have pi n and then you're subtracting pi, you don't need the negative pi, right? It's like even numbers are 2n and then minus 2. Well, yeah, that's still going to produce an even number as well. So in this case, I left it in there, where in the last example, I dropped it off. So, because what happens is when you multiply by 2, to get rid of the 1/2, you get negative 2 pi plus 2 pi n. So you can see that's redundant, so therefore we drop it off there. So it doesn't matter when you drop it off, you're still going to get the vertical asymptote needs to be x equals 2 pi n. And let's just do the domain. So the domain is going to be all real numbers such that x cannot equal 2 pi n. All right. So now let's just do these last 4 questions, guys, and then we are done. So I see a negative, so therefore I know that's going to reflect the y-axis. The period, again, is going to be pi divided by absolute value of negative 4, right? Remember, it's absolute value b, so that's just going to be pi over 4. The range here is going to be negative infinity to infinity. I don't really know why I wrote to do the range because it's always that, right? Never changes. But the vertical asymptote is going to equal negative 4x is equal to pi n. Okay, so you divide by negative 4. And you could say x equals negative pi over 4n, which is true, which is correct. Typically, a more simplified answer would just be the positive version of that. Again, I'm not going to mark my students down wrong for this, but we look in a more simplified answer, or at least on a multiple choice, you would expect to see that in the positive version. And that is it, right? Yeah, it is. Okay. So one thing that students, also kind of forget about is like, what does this 3 do? Well, again, the 3, vertically stretches the graph, right? There's no amplitude for cotangent or for secant or for cosecant because there's no absolute max and min, which is one thing I forgot. These graphs are unbounded, right? Since the graphs are unbounded, there is no amplitude. Because remember, the definition of amplitude was the half distance from the max to the min. Sorry, I had to add that in because I totally forgot about it. All right, so in this case, we just have period is going to be pi divided by 3. That was easy. Pi divided by 3. No other transformations. You could say a vertical stretch if I asked for it. The range is going to be negative infinity to infinity. I guess I should have shifted one, down one, but yeah, why don't I do that? Why don't I just do a +1? Just change that. So therefore I could do a vertical transformation of up 1. And then I could say my vertical asymptote is going to be x equals, oops, I have a 3x. You know what? That's what I should do. Maybe I should do, I'm going to change that. Let's see, what do I want to change that to? Do I have one of those in here? I didn't do one of those, did I? Yeah, let's do that. Did I do enough here? Okay. So I'm going to do this as a 3/2. Okay. So let me actually change this. So I'm going to change this problem. Sorry about that. All right. So the period is going to be pi divided by 3/2. Again, multiplied by reciprocal is 2 pi over 3. There we go. So now I have 3x over 2 equals pi n. So therefore x equals 2 pi over 3n. Okay. And there you go. So I just want to kind of make it a little different because none of these that I kind of changed here. Here I'm going to have a vertical compression. My period, there's nothing in front. So therefore that's just going to be pi. I am going to have a phase shift as pi over 4 to the left. My range, again, is -infinity to infinity. My vertical asymptote, though, in this case, is going to be x plus pi over 4 plus pi n. So if I subtract the pi over 4, oops, not plus pi n, equals pi n. Okay, so therefore x equals negative pi over 4 plus pi n. And again, if you wanted to kind of simplify this, if you add pi to it 1, like let's pretend n is 1, like negative pi over 4 plus pi would be positive pi over 4. So I could, actually, I'm sorry, 3 pi over 4. So another answer could be positive 3 pi over 4 plus pi n. And again, I just wanted to show you because typically we like the smallest positive as our simplified answer. And so if you were to see this on a multiple choice problem, you'd probably see as this is the answer choice rather than that. So you just want to make that connection that those are exactly the same. The last example here is I have a 2 in front of the x, so therefore I need to factor it out, which is again dividing out of 2. Again, 2 does not evenly divide into pi. So rather than think of how do I divide 2 into pi, you can just say, well, dividing by 2 is the same thing as multiplying by 1/2. I can multiply pi times 1/2. Pi times 1/2 is just going to be pi halves. But let's rewrite it here. So we have y equals cotangent, factor out the 2. That's going to be left with an x minus pi halves. And if I'm concerned or not sure if I did that right, I just multiply back. 2 times x is 2x. 2 times negative pi halves is negative pi. So now I have my period is going to be pi divided by 2. I have a phase shift, which is going to be pi halves to the right. And I have a vertical shift, which is our vertical translation, which is down 3. My range is -infinity to infinity. And then my vertical asymptote is going to be 2x minus pi equals pi n. And I think actually, never mind, I already did a problem like this. So therefore I have 2x is equal to, oh, I don't need that extra one. Is it going to equal pi plus pi n? Again, you don't really need the pi, so we just have 2x is equal to pi n. And then divide by 2, x equals pi halves n. And there you go, ladies and gentlemen. That is how you identify the characteristics for your cotangent, your secant, and your cosecant. I hope you enjoyed, and I hope you helped out your graphing. If you have anything that you'd like to add as far as what you understood or what you had trouble understanding, please feel free to leave a comment down below, and either I or somebody can hopefully help you out. Look forward to seeing you on the next video. Cheers.